Thank you all for coming. So in this talk, I'll argue and demonstrate that integrating artificial intelligence and virtual reality, and also anthropology, which is my original background, alongside neuroscience can drive advancements in both scientific understanding of the human mind while developing more human-centric and culturally aware technologies that can hopefully give us a better world and society. Oops. So, as I mentioned, I'm going to be talking about the integration of some fields that have typically been kind of far apart. So I'll bring in anthropology. I think it's important because it's allowed me to explore the implications of these technologies in terms of human evolution, cultural diversity. Neuroscience approaches have allowed me to look at the neural foundations of perception, emotion, learning, memory, decision-making. And VR and also augmented reality, AR, has allowed me to simulate complex environments and study human responses. And AI, most recently, is providing me a key analytical tool that has allowed me to uncover much deeper insights than I was previously able to do and people have thought possible. So, as mentioned by the introduction here, I run a lab at University of Pennsylvania. It's called the Virtual Reality and Artificial Intelligence Lab, VRAIL. And we have quite a few different services. We work with a bunch of different groups. Today I'm going to give some examples of our projects, the ones that highlight the intersections that I mentioned. And I'm always happy to hear from anybody that is interested in hearing more about our work, getting ideas, collaborating, needing tips. Just reach out. I am here. I'm happy to talk. I do have a summer intern program, and I do teach classes at University of Pennsylvania as well. So there's lots of opportunities to get involved in this sort of thing if you so desire. So I imagine most of you have some idea of what a virtual reality headset is like, what it's like to wear one. But I use it as an experimental platform. It allows me to do advanced spatial analysis. And I've been doing this since about 2009 with the earliest headsets. And the kinds of spatial analysis I began with were initially kind of cultural and focused on how people perceive each other and their environment. And it allows us to do a bunch of things like qualitative and quantitative gathering, data gathering. It allows us to track people's movement, specifically their hands, their eyes, their heads, and even their legs, if we put devices on their legs. Much more recently, we've been able to track things and very small things like pupils, pupil movement, people's cognitive load, and even their emotive states. Augmented reality is similar. For those of you that have tried it, it can be also fun and also interesting. It is much earlier in its development stages, but it also allows us to get eye tracking data. One of the benefits of it is fully portable. It allows people to move around much more, and it allows us to explore how people interact with objects that are not actually there, holographic objects. And you can see here the HoloLens, Microsoft's headset. We have a bunch of applications that we use this for, and many of them are medical-oriented, and we have some that are forensics-oriented. And they allow us to experiment in ways that is not possible in real life or possible in VR. And that's mainly because you could still see what's going on out in the real world. So AI allows us to do a bunch of things that pair very well with the kind of qualitative and quantitative analysis that we are doing in virtual reality, augmented reality. We are using LLMs, things like ChatGPT, but we're using llama models, we're using natural language processing, and we are using a variety of different kinds of machine learning techniques to understand behavior, to understand how people are responding to their environments. And we're also using some visual artificial intelligence techniques like neural resonance fields to help us create environments. So I'm going to go through this kind of quick because I've lost a little bit of time. I'll give you a brief background of my research so you can kind of see why I've taken the perspective in terms of integrating anthropology, neuroscience, virtual reality and augmented reality and artificial intelligence together. And then I will discuss some of the current projects that I'm doing that I think highlight the importance of these connections. And I'll wrap up with the main funded project that I am working on right now, which is a neuroaesthetics project, which really highlights the incorporation of all these different perspectives. So as I mentioned, I got my start in anthropology and archaeology. I worked in the Maya region in the Yucatan Peninsula. I specifically focused on looking at the early Maya people before they had writing systems, when they started building their temples and settling the coastline. And I started doing this actually in 2008, and I published research using virtual reality. Of course, I didn't have a good headset, but I could do it on the computer in 2009. I worked at a site named Cerros Belize. This is known as one of the most important early Maya sites. You can get an idea of what their religion was like when it first began, what their architecture was like, and what they were doing. And I was very interested in understanding what was going on in their architectural environment, but what was also going on in terms of their rituals, their behaviors, their beliefs. And one of the earliest pieces of architecture you could see here, it's a structure named 5C Second. It is a pretty big temple right on the coast, and it is very well known because it has these giant mask facades on the front of it. And there was many different theories about why the temple was built where it was, right in the path of hurricanes, why they put these giant figures on the temple, what these figures meant. And as I said, this was before the Maya people had writing, so people had to interpret some of the symbols, the beliefs, the orientation of the architecture, and there was no real answer to why they built this building as they did. There was a general kind of answer, oh, it had to do with maybe this god, that god, but nobody really knew. So I thought maybe virtual reality can help me make this happen. So as my research moved along, I eventually was able to acquire a virtual reality headset, the early Oculus developer kit, and I converted the archaeological data, as you could see here, the archaeological maps, into 3D with the idea that I could import this into virtual reality and get a better understanding of what people's experience was like, what they felt, what they could see. And I used, back then, something called CryEngine, which is what Crysis, the video game, was built on, and the original Oculus dev kit. Things were very difficult. This was back in 2014, 2015, to get it just to even run on this headset. The software was not there. It's much easier now. And this is sort of what it looked like. And I used this technology to create sort of like a time machine, to try to understand what the architecture would have looked like 2,000 years ago for the Maya people, what that temple would have been used for. And I found that there were some very interesting things that sort of jumped out at me when I looked around the virtual reality environment. So what I did is I moved the sun, the stars, because I knew the Maya were very interested in astronomical events, and looked for potential alignments, alignments with architecture, alignments with where people would look around their environment, and I found one. There was a specific day of the year, May 15th, May 14th, and this is right on the coast of Belize, where the sun would rise, as you can see here, from the water. It was the first day the sun would rise from the water. Before May 15th, the sun would rise from the land. And the only place where you could see this event was right where that temple was built. So they built this temple at this place where they would look out on their environment, and you can see it here on Google Earth. This alignment happens where the sun lines up, its sunrise lines up with the coastline. And May 15th, so what? Why were they interested in that? Well, it turns out today, still the Maya people, they're still alive, they're just not building giant pyramids. Still today, the Maya people pay attention to May 15th. It means you have 2 weeks left before the rainy season comes. You have to have your corn in the ground and planted. Otherwise, it's not going to grow right. It's going to get swept away by the rains when they come, or maybe the animals will eat it. So still a key day. So 2,000 years ago, the people were paying attention to their environment closely and then building a commemorative temple to honor this sort of encoding of the landscape. So as you could see here, it would have been easy for them, once they noticed this alignment, to say, okay, the wet season is when the sun rises over the water. The dry season is when the sun rises over that spit of land, the jungle right there. So the temple that gets built, that we never knew what it was for, I think this is what it was for. It was a commemorative monument for this place where they could look out, where it helped them learn how to survive. And I found that this was a great story, a great interpretation, but I wanted more. I wanted to understand the details of the human mind, the complexities of human experience in a more precise way. So I went to neuroscience, and I found that there were tools to do this, and there have since been more tools developed along the way that have made it possible for me to understand human experience and the human mind in a fine-grained manner. So we utilize many of these tools in the lab here, and we've put together quite a few different applications that are exploring things in an anthropological neuroscience type way. One of the apps that we're currently developing right now for the Apple Vision Pro using the high-resolution headset, the tracking, is a evolutionary focused or inspired application that aims to uncover if there is a subconscious, autonomous sort of neural mechanism for monitoring your environment. So what we're going to do, it sounds a little bit freaky, is we're going to fire pulses into the back of people's brains, measure their response, and modulate their environment to different survival conditions using the Apple Vision Pro. And we're using a technique that was based on a light field technique developed by Google in 2016. It's called Google Soret. They abandoned it, but I found I could rewrite the shaders, and it allows us to create high resolution, very high detailed ray traced environments that can be imported into the Vision Pro, or even something like the Oculus Quest 2. Another app that we have recently published on is a forensics and surgical science app. This is where CT scans, we use a technique called neuroresonance field scanning to import real skeletal materials into virtual reality or augmented reality. In the case here, you see the HoloLens. And this allows us to examine and identify fractures. It allows surgeons to practice on people before they actually go to the operating room, which has the benefit of reducing the amount of follow-up surgeries that people have. But it allows my colleagues that are forensic science to explore the forensics material. As you can see, skeletal remains here, anywhere in the world, no matter where they are. They could bring their expertise in, and in a way that will not destroy the skeletal material. Most of the time when forensic scientists are dealing with a body that they found, they have to deal with it disintegrating and then being lost and not being able to identify it. But this allows them to preserve it and focus on their analysis. And we're using techniques like eye tracking to record and monitor how the surgeons are using these techniques for practicing surgery, and also how the forensic scientists are identifying specific elements of fractures that they have to use to identify individuals. Another thing that we're using that is potentially has far-reaching application beyond anthropology or neuroscience is cognitive measures to understand how people are trained in virtual reality and augmented reality environments. So we're using measures like cognitive load, eye tracking, to understand what difficulties students or even people like the military will encounter when they are undergoing training with physical and virtual objects. We can use eye tracking and a variety of biometric techniques like galvanic skin response to see what stresses people out, what is a problem in the training perhaps, what is an effective training technique, and we can constantly use artificial intelligence to monitor people's performance as they are being trained. And this is something that's in development and we're working on funding for. So it's coming soon. We also have techniques to represent, let's see if we can play it here, to represent radiation fields. So radiologists, whenever you have to get an X-ray or something else happens to you, you have to go see a radiologist. They're going to scan your body. They deal with a ton of radiation every day. And this is a problem. It adds up over a lifetime. So we are creating augmented reality techniques that will allow them to view simulated radiation fields so they can avoid these things and perhaps avoid some of the negative consequences. And you could see here it's pretty gross stuff. And we're using Unreal Engine, you can see on the left, to simulate the radiation spread. Unreal Engine has an advanced enough lighting engine. You can see it here with its ray tracing. It's showing where the radiation bounce potentially could occur, where you would get hit if you were a radiologist doing your testing and studies. We are exploring the use of metahumans. This is another Unreal Engine technology alongside eye tracking. In many of our studies, we've found that people have certain behaviors, certain things that we can track that allows us to understand how they may have a bias towards certain individuals. And most of the studies that we've had to do have been with two-dimensional pictures, but the metahumans allows us to have three-dimensional, fully virtual reality or augmented reality humans that can be configured in any way that we need. So one of the things that we've found is that people with certain types of scars are treated differently. We can manipulate the metahumans and create different hypothetical scarred people and see specifically the amount of scarification, for example, that would be required for somebody to have a bias, an implicit bias towards another individual. One of the other apps that we've recently put together, and it was actually released for West Philly, is a augmented reality, and this one's for the phone, flu vaccine app. This is an application that is community focused, so we're working with the community in West Philadelphia, and we've created an app that teaches people about the flu vaccine, the benefits of it, and allows them to make their own choice about it and potentially sign up and get vaccinated. And it's got a little game to play too that's sort of like a Pokemon Go. And the idea is that people play the game, they get quizzed a little bit, they're not as afraid of the flu vaccine. So you can see it's got a little Pokemon-like flu character. And it's passed out on cards and posters. So people hold up their phones and they can see this game here. And it's just a little mini game, but we've had very favorable response to it so far. And yeah, you probably would recognize this scream, the Wilhelm scream. And the project that I've just received a bunch of funding for right now is a neuroaesthetics project. So probably many of you are not familiar with neuroaesthetics, but this is a field that has recently developed that has focused on how people have aesthetic responses to art, architecture, the human face, and objects. And what the idea is that we can measure people's neurological response to these things, art, architecture, faces, and understand why people like things or understand why people don't like things, why they feel safe in a place, why they feel afraid. And these things are very, very important and I think have some big implications in terms of architecture. Well, we're always inside architecture. We live indoors most of our lives. This has an impact on our cognition, our creativity, and our health. So the focus of neuroaesthetics is, as I said, understanding the neurocorrelates, to understand what's going on in the brain, but also the psychological effects of these architectural spaces. So we are currently designing working through a set of experiments that are testing people's response to different architectural environments in virtual reality and non-virtual reality. So we are comparing to see people's psychological response to virtual reality. And so what we're doing is we're using advanced 3D scanning, Unreal Engine, and this allows us to reconstruct real environments in a way that is aimed to mirror the test environments that we have in our laboratories. To understand people's psychological responses, we're using different techniques of natural language processing. And these techniques have allowed us to identify correlates of emotion and responses to what are more or less a sort of architectural essence, the key elements or key responses to architectural space that we all, it's been shown that we all have. And so right now we're running through the test and working on the analysis. And the idea is that we're hoping to understand the precise differences between virtual reality and non-virtual environments. And nobody has actually fully tested or explored this yet. Virtual reality headsets have been around, since the 90s, and consumer ones have been around since 2014, Oculus or whatever, but there's been hardly any or very few studies that have empirically measured the differences and similarities between virtual environments and real environments. So we aimed to fully explore this, to precisely explore it, and once we do that, then we believe that we can have a simulation platform that we can use to test other theories and to fully understand what architectural space can do to the human mind. So some of the ratings that we have here, and they actually, I think, make a lot of sense, that we've found using natural language processing that the architectural spaces have is there's a triad of three. So the first one is coherence. This is how pleasing an architectural space is, but how organized it looks. You could imagine a church. It would look organized. You know, it would be a big open space, and you can see the pews or whatever. It is a very organized space, and there's a reason why it's organized. The designers of the church wanted to represent maybe order as opposed to chaos in the cosmos. But we found that there's actually a specific neurocorrelate when we've done MRI scans or fMRI scans that is triggered when people see coherent architectural spaces, spaces where there is a focus on order. The second is hominess, and this is one that we're all familiar with. When you go home and you feel at home in your architectural space, there is a sense of hominess that you have. This is a sense of personal relaxation, comfort. And this is very different than coherence. You maybe have a house that is organized, but it's not going to be organized like a public space. It will be a space that is specifically organized to you. Maybe the lighting will be dimmer. Maybe you'll have some personal effects. It'll be smaller. It'll feel cozy. This is hominess. And once again, we've found that there is a specific neurological correlate, part of the brain, that fires when people look at and experience homey architecture. And the last of the three is fascination. And this is architectural spaces that are very complex. They're very fascinating, very interesting, where there is a lot of information density. Once again, another neurological correlate goes with this. And an example of this would be, like a Chinese garden. You go in there, and there is an abundance of plants, paths, all these things that capture your attention and keep you focused on exploring and looking around your environment. So all three of these things, in our architectural spaces, we have a kind of a mixture of these things. And our brain is firing for each one of these in kind of a different way. So you wouldn't say a church is only coherent. A church maybe would have a high element of fascination as well. Maybe it's very ordered, has an ordered space in the middle, but the back wall of the church has facades, intricate carvings, and it is very fascinating. So these are the metrics that we're using to understand people's response to space. So we're using that in tandem with virtual reality environments, seeing how people react in these terms to virtual reality spaces, comparing that to non-virtual environments, so scanned virtual compared to real environments. And we are also gathering, as I mentioned, qualitative data, so free response data. We're allowing people to say what they feel, what comes to their mind, how they feel about these architectural spaces. And many scientists have shied away from this kind of data because people say all sorts of crazy things, and it's very hard to compare. But psychologists have found and anthropologists have found that free response data can give us very, very rich information that surveys cannot give us. That said, how do you deal with this data? So we found that artificial intelligence can boil down this subjective data and allow us to take this qualitative, very rich data and convert it to quantitative data. And we're incorporating a bunch of different techniques to make this possible. So there's a field out there called sentiment analysis. We are taking the most cutting edge approaches and working towards an emotion analysis alongside the sentiment analysis. And we're using different Python techniques alongside Llama 2. Well, Llama 2 is the model that's like ChatGPT that Meta released for free. We have to use Llama 2 because our our data is encoded. We have to keep the privacy of our test subjects private. And Llama 2 is actually working a lot better than I thought it would. It allows us to reduce this very complex, rich data down to something that we can analyze and replicate. And what is that? What does it look like? Well, I call these perceptual effect networks. So by boiling down this data, combining it together, we can see that there are certain psychological effects that end up being networked, or they appear as networks, transformations of emotions. So emotional states that can move from one state to another and are interconnected. These perceptual networks, maybe they look neat, but what is the point of them? What do they get us? They allow us to understand how people's psychological state transforms from one state to another. And this allows us to be predictive. We can predict how people are going to feel. If they feel X, Y, Z emotion, they are going to feel A, B, C emotion. And this allows us to understand the causal relations between emotions, but it also allows us to see the causal relations, what the architectural space is doing to people. And we're using some new techniques like graph neural networks, and this allows us to predict how people are going to respond to spaces that they've not even been tested in yet. So, what is this good for? Well, of course it's good for architecture. Architects often build architecture and they never actually test people to see how people feel about it. But with this sort of approach, architects could build virtual architecture and then test it on people and see how people are going to feel and predict how people are going to feel. Of course, this would work for art. People could produce art and have a better understanding. So all of our techniques are also being applied to people's experience in art museums as well. So we're using the Penn Museum and the Barnes Museum here in Philadelphia and trying to understand what people's aesthetic responses are to artworks and museum spaces. Of course, this would be great for design. I have a bunch of design students that are using these similar approaches. This would be useful for education and training. If you have an idea of people's psychological affect, their states, their emotion, their well-being, yes, you could make them, you could help and aid their training. This would also be useful for UX design. A lot of UX designers have an idea of what their subjects or their users are going through, but they don't have a precise idea of the emotional content of their experiences. With this, they could eventually predict this. And I think there's many more applications that could be derived from this. And thank you. Yes?
Hi. Great talk. Thank you so much for this. This was really insightful. With regards to like architectural renderings and things like that in the virtual space, is there any phenomenon similar to like uncanny valley that people experience and that biases them when they look at these environments?
So yes, that's a good question. And uncanny valley is something that I have wanted to explore in more detail, especially with like the Apple Vision Pro set and the personas. We're running into the uncanny valley every day. But in terms of architectural space, yes, there are things that are uncanny to people. It's not been defined in the literature, but so an example, in the early phases of our testing, I can go back to it up here. We have a test room here that is aimed, so the one on the left is the virtual one, the one on the right is the real one. When we first built the virtual one, there were I tried to replicate the details with the scanning, but there was a few little details that I missed. Of course, you could see the shadows are there, the light's there, all those kinds of things. But I missed the doorknob. And I thought, oh, it won't matter. They're not going to go outside the testing room. But so many people missed the doorknob that it totally threw off the experiment. And we had to start all over. Sometimes little details like that totally freak people out. And when we looked at the subject responses of what was going on, everybody said that they felt trapped, even though they were never supposed to leave the experiment. So small little details can shift people into an uncanny place that I hadn't really expected. Something like a doorknob to a non-functional door.
Cool. Thank you.
So small little details that I can't exactly explain, but it's good to be as precise as possible with your reconstruction because people will notice.
Nice. Thank you.
One of the things that you were talking about, you're looking for causal things and you're modeling and doing predictive things. Did you find any did you do any modeling of how the personality inventory of the tests of the human test subjects affected that? Like I've got 3 engineers and 3 artists and that sort of thing.
So the way that it works is we have, for our test subjects, we have a pool mainly of students, but other people can sign up for it. So it's more about eliminating people that are not from a general population. So anything like if we had somebody that was a virtual reality engineer, they would probably notice these little details all over the place. We wouldn't allow them to participate in the study. But I think your question is a good one because I do think that different people with different specialties would have different perceptions of their environment. And we have found with our art studies that art specialists do have completely different aesthetic responses to artworks than, just for example, students. They rate the artworks in a different way, they have a different vocabulary, and they appear to have a different aesthetic response in terms of whether or not they like an artwork or not, just based on having knowledge and a background in like art history, for example. So that's something I would like to explore, especially in terms of architecture. Good question.
Thank you. Just to follow up on his question, how would you normalize that data to actually have a consistent analysis?
So that's a good question. Norming and normalizing the data is tricky. So when we have people come in, they have to answer a series of survey questions. And more or less those survey questions will be things that will eliminate their data or not. So for example, if they are from another country and they don't speak English natively, they might not understand the questions in the same way. And oftentimes their responses show that they do, and sometimes you can't really tell. So the pre-screening process is what is supposed to produce normalized sample data. And we also have a post-screening process as well, where we ask people questions that are more subtle about what they remember, what they don't remember. And if people, for example, remember a bunch of things that weren't there, then we know, okay, maybe this person's either not paying attention or maybe there's something else going on. It's not a perfect approach, but with any analysis that we're doing, we did 100 subjects, 100 for the virtual room, 100 for the non-virtual room. It's a statistical sample that we believe has enough statistical power to weigh out any outliers. And that's something we have to go through when we're doing the analysis too. If somebody's off the charts doing something weird, then yeah, we might have to look into the data more carefully. Good question.
Sorry, one more question about the demographics of your test subjects. They're all college students from UPenn?
So yes and no. So most of them are college students. And with most psychological studies, that's sort of how it ends up working out, because you have all these students walking around. That said, we're not requiring them to be, and we do get people that come in, because they could sign up on a website. There's a website called MindCore, and you get paid $20 to do this. People can sign up, and we do get non-college students. We have participants, we've had participants as old as 78 tried these things out. They were quite impressed by it. But yes, it's not a perfect system, but that's sort of how the majority of psychology and neuroscience testing is done. We are getting a sample of mainly healthy, well-to-do, smart individuals.
And just one more question. Are you able to use this to help figure out how to build things, like architecturally, not just visually?
So that's the goal. The goal here is that we can get a good baseline, understand people's experiences, and then start modulating the virtual environments. Say, add windows, have very big windows, have small windows, see people's responses, so that we can build things in virtual reality first, see how it affects people, and based on those tests, then go out and build it in real life. And we have a study where we're working with a drug rehab center, and we're working towards finalizing a virtual reality environment and then building that in real life so that the people that are there have what we call a biophilic refresh room that hopefully will have the best psychological affect on them.
Maybe you addressed this in some form and I didn't catch it, but is there, I think there's a Venus flytrap in that picture, for example.
You caught that.
So if someone, I have not used virtual reality very much, but I feel so I don't know, but I feel like I would have a more muted response to seeing a Venus flytrap in a virtual reality environment than in real life, for example. I wouldn't be, viscerally. So do you have something, do you find that that's consistent in comparing the results from the real and the virtual, or?
So to answer your question, that's an Easter egg in there from Mario. But in the real environment, we do have people that have had no experience in virtual reality, and I would say most of the subjects, even though virtual reality's been around for a while, you can go out and get a headset, most people have had very little experience. So there is a wide range, I still find, in people's response to virtual spaces. We get people that are like, oh, wow, I'm tripped out. I feel like I'm in the Matrix. To, I feel like I'm in Minecraft. To some people that have a very muted response, they just kind of regard the virtual environment as though it's a regular environment. So what we do to try to get towards that more muted response, because we want to see how people regard it as a real environment, is we make them do a bunch of super boring psychology tests for about 20 minutes on a virtual computer in virtual reality. And then most people kind of forget that they're in virtual reality because the environment is real enough looking. They're doing things that they normally do when they come take these tests or whatever. And then once the tests are over, then we start asking them about it. And then the goal is that they're kind of regarding it as their regular environment. And most people, when they take off their headsets and they're pushed up against a wall or something, we have to be safe. We don't let people move around much. They're like, oh, wow, I totally forgot I was here. So I think it's successful in that regard if we can get that to that muted response. And we're testing very normal environments currently because the goal is that we can use this as a tool to build real environments and understand people's response to real environments.
Okay, thank you.
Would you be able to comment on the time that somebody spends in an environment to get that response, like that initial emotional response versus if they had spent a longer time in that environment, and if that response changes, and would that have affected the type of architecture? Maybe working in an office, oh, it's nice, but after working in there for 2 months, I'm like, I'm sick of this place. So have you found that type of like evolving on a particular feeling towards an environment?
So as of now, we put people in there for about an hour. So it is these short chunks, and we're testing many people. And all I can say so far is that some people, right away, they just act like it's their real environment. Some people act like they're tripped out or weirded out. And then everybody takes the test, the boring psychology tests that are just like, click this, answer this, what word can you think of here? And I would say 90% of them, after they take those tests, then they're treating it like a real space. There's still some people that are just like not going to believe it no matter what. They look for little glitches, or they swing their head around so fast that they mess up the perception that, you know, the headset's on or something like that. But it is something that I would like to explore, what a long-term kind of affect would be of working in a virtual environment. And we originally built these environments, there's a little backstory here, to see what the perception of being in an environment that has plants in it would do to people. So that's why you see that there's these green walls in there, because there's the biophilic hypothesis that having plants in your environment will make you more creative, make you healthier. We did not see a significant boost in creativity, but people said they felt better by being with the plants, even being in there for an hour. So to really understand those long-term metrics, it is tricky to do, and it's currently something that we're not, we haven't been able to do that. But we will get to a day where, yes, we can put somebody into VR for a week. The headset will be light enough to not bother them, and we can have enough grant funding to pay them to be in there for a week. And to see, okay, you know, what happens over that amount of time. The day is coming, regardless if we believe it or not. I think the headsets are going to get lighter, smaller, and that kind of testing will be feasible. Right now, the Apple Vision Pro, super great headset, very sharp graphics, visuals, but it's heavy as hell, and people can't wear it even for more than an hour. So technology as well as practical limitations have prevented us from exploring that. But that's something I would really like to explore. Yeah.
During your talk, you mentioned being able to track people's cognitive load, and I wanted to understand, like, what are some of the indicators that help people understand somebody's cognitive load?
So this is a kind of a new thing that a few companies and a bunch of research has recently explored. HP has developed a system where it integrates blood pressure, eye tracking, as well as downward-facing cameras that measure your mouth, your expressions. And the idea about cognitive load is more that you are trying to compare what somebody is doing and as well as understanding their stress. So if they are more stressed, their eyes are flitting about, they have higher blood pressure, their lips are pursed, then you would say, there's probably more cognitive load. That this is a more maybe tricky exercise for somebody, that they're maybe being asked to remember too many things or do too many things. It's more about that. So most of the metrics are, I would say, about how poor people are doing or what the challenges are that they're facing. We don't have too many metrics, unfortunately, for how good people are doing until we test after the fact and say, oh yeah, how much did they remember? How creative were they in problem solving? And things like that. All right, well, thank you all for coming.